Assalamu alaikum sir. I am Digonto Shautal, Rule 51. Today our group will present a data structure called Trie. A trie is a special tree-like data structure that is used to store and search words efficiently. It is especially useful when we need to search words based on their prefixes, such as autocomplete suggestion in search engines. In the first part of the presentation, I will discuss the origin of Trie, why we need it, how it works, and some of its real-world applications. Before learning how Trie works, let's look at its history. The idea of Trie was first described by the Norwegian mathematician Alex Trie in 1912. Later, in 1959, René de Le Brindis suggested using it in computing. In 1960, Edward Fredkin introduced the term Trie. The word comes from the word retrieving, which means finding or retrieving information. Trie became very popular in the 2000s when companies like Google started using it for autocomplete features. When we type a few letters in Google search and suggestions appear instantly, Trie is one of the data structures that can help make that possible. Now let's discuss why we need Trie. Traditional data structure such as array and hash table have some limitation when working with strings. In an array, if we want to find all word string with a specific prefix, we may need to check every sorted word one by one. Hash tables are very fast for extract searches, but they do not keep the character by character structure of a word. Because of this, prefix searching becomes difficult. Also, words such as car, card, and care share common letters, but array and hash table share them separately, which can waste memory. Trie was designed to solve those problems. Trie short word character by character. Each character is represented by a node, and words with common prefix share the same path. For example, the word car, card, and care all share the characters C, A, and R. Instead of sorting those characters multiple times, Trie sorts them only once. This saves memory and makes prefix searching much faster. Another advantage is the search time depends mainly on the length of the word, not on the total number of words sorted. Now let's look at some important characteristics of Trie. Every Trie starts with a special node called the root node. All operations such as insertion, searching, and deletion being from this root. Words that share common characters also share the same nodes. The depth of the Trie depends on the length of the longest word sorted in it. Because of its structure, Trie is very efficient for sorting and retrieving strings. This slide shows how a Trie is represented. Instead of creating separate paths for every word, Trie reuse the same nodes for the shared path. This reduces memory usage. The color terminal nodes indicate where a complete word ends. So even if multiple words share the same path, try can still identify each individual word correctly. Try has many practical applications in real life. One common use is autocomplete, such as Google search suggestion. It is also used in code editor to provide code completion suggestion. Phone contact search and GPS address lookup often use try as well. Spell checkers can quickly determine whether a type word exists in a dictionary. Try are also used in computer network for routing data and in word game like Scrabble. Because of its fast prefix searching capability, try is widely used in systems that handle large amount of text data. Thank you. This concludes my part of the presentation. Now I will hand it over to the next part presenter.
Hello sir, Assalamu alaikum. I'm Monisik Trie. My role is 2024831053. In this part of this presentation, I will explain the trie node structure and the main operation of a trie, which are insertion and deletion. So here is the node structure. A trie is made up of many nodes. Each node contains two important things. The first one is an array called children with 26 positions. These positions represent the 26 letters from A to Z. The second one is a Boolean variable isleaf called isleaf. The isleaf variable tells us whether a complete word inside the node. Initially, all child pointers are set to null because no child nodes are exist yet. Also, isleaf is set to false by default every time it starts from a special node called the root node. The root node acts as the entry point for all operations such as insert, search, and delete. So this is a trie operation and node declaration. A trie mainly supports four operations: insertion, delete, search, prefix, and prefix search. On the right side of the slide, we can see the trie node declaration in C++. Each node stores 26 child pointers and one Boolean flag called isleaf. This design allows insertion searching to be performed efficiently. The necessary libraries used in this implementation are irstream, vector, and string. Now let's see our now let's see how insertion works. To insert a word, we start from the root node, then we process the word character by character. For each character, we check whether a child node already exists or not. If the child node not exists, we create a new node, then we move to that node and continue with the next character. After all characters are processed, we mark the final node as a leaf node by setting each leaf to true. This indicates that a complete word ends there. During the insertion, sometimes part of the word may be already exist in the trie. For example, suppose we have already inserted the car with the word car. Now we want to insert care. The path for C, A, and R are already exist. So we don't create nodes for these characters. We simply follow the existing path and add the new character E. The same idea applies when inserting word car. This sharing of common prefixes is one of the main advantages of a trie. If a required, so this is new character actually path. If a required character path doesn't exist, we create a new node. For example, we when inserting the cat word cat, if the characters are not already present, new nodes for C, A, and T are created. Then the last node is marked as a leaf node. This allows the try to store the new word successfully. So here we can see this slides show a visual example of insertion. First, the word cat is actually inserted. Nodes for C, A, and T are created. Then the word car is inserted. Since C and A are already exist, only the character R is added. Next, the word card and care are inserted. Again, the common path is reused and only the new characters are added. This demonstrates how tries save memory by sharing common prefixes. This slide shows the actual insert function in C++. The function starts from the root node, then it processes each character of the word. If a child node doesn't exist, a new node is created. The current pointer moves to the next node after each character. Finally, the last node is marked as a leaf node. This completes the insertion process. Here is the delete process operation. Now let's discuss deletion. To delete a word, we first follow the path of the word from the root. After reaching the last character, we remove the word by setting isLeaf to false. Then we check whether the node has any children. If it has no children, the node can be deleted safely. The algorithm then moves backward recursively and removes unnecessary nodes. Deletion stops if a node belongs to another word or if it has another children. In this example, the words are car, card, care, and cat. We want to delete the word car since card and care still use the same path. Those nodes cannot be removed. Only the leaf mark of car is removed. The shared nodes remain unchanged. This ensures that the other words are not affected. In this example, the words are cat and car. Now we delete cat. The node representing T belongs to only to the word cat. Since no other words use this it, the node can be removed completely. This frees memory and keeps the try clean. This slide shows delete function in C++. This function works recursively. It first reaches the end of the word, then it removes the leaf mark. If a node has no children and is not needed by any other word, it is deleted. This function continues moving backward and removes unnecessary nodes. This process ensures that only unused nodes are deleted while shared nodes remain safe. That context my part of the presentation. Thank you for listening, sir.
I am Muhammad Adil. My role is 66. Now I'll continue from here. I'll explain the search operation in a try. To search for a word, we start from the root node and process each character one by one. For every character, we check whether a corresponding child node exists. If a required path is missing, we immediately know that the word is not present. If all characters are found, we finally check whether the last node is marked as leaf node. If it is marked as leaf node, the word exists in the try. There are two possible cases when we perform a search. The first case is when the complete word exists. In this situation, every character path can be found successfully and the last node is marked as a leaf node. Let's look at an example. Suppose the words cat, car, card, and care have already been inserted to the try. Now we search for the word car. We follow the path C, then A, and finally R. Since the node R is marked as a leaf node, the try confirms that car is a complete stored word. So the result is found. The second possible case is when the complete word does not exist. This can happen in two situations. Either a required path is missing or the path exists but the final node is not marked as a leaf node. Here we are searching for the word CA. The path C to A exists, but because other words such as cat and car starts with these letters. However, the node A is not marked as a leaf node. This means that CA is not only a prefix and not a complete stored word. So the result is not found. Now let's look at the implementation of the search function. The function takes two parameters, the root node of the try and the string we want to search for. First, we create a pointer and set it to the root node. Then we use a loop to process each character of the string. For every character, we check whether the corresponding child node exists. If it does not exist, the function immediately returns false. If the child exists, we move the pointer to that child node and continue. After all characters have processed, the function checks the is flag of the current node. This ensures that the search string is a complete word. Now let's move on to prefix search. Prefix search works almost exactly like normal search. The main difference is that we do not check the leaf node at the end. Instead, we only check whether the prefix path exists in the trie. If the path exists, the result is true, otherwise it is false. Let's look at an example. The words cat, car, and care have all been inserted into the trie. Since all of them begin with the prefix ca, they share the same path from the root to c and then a. When we ask whether any word starts with ca, the trie simply follows the path and confirms that it exists. So the answer is true. Now consider the prefix xyz. No word in the trie begins with the letter X. As soon as the trie checks the first character and finds that no such path exists, it immediately stops searching. So the answer is false. This shows how trie avoids checking every stored word and saves time. Now let's look at the implementation of the prefix function. The beginning of this function is almost identical to the search function. We create a pointer start from the root node and process each character of the prefix one by one. If a required child node does not exist, the function immediately returns false. Otherwise, we continue moving through the trie. The key difference is the last line. Instead of checking is the function, the function simply returns true. This is because prefix search only checks whether the path exists and does not need to verify if it is a complete word. This slide shows the input and output of our trie program. First, we insert words cat, car, card, and care, and the output confirms that they were inserted successfully. Next, we search for car, and since it exists in the trie, the result is found. Then we search for CA. Although it is a valid prefix, it is not stored as a complete word, so the result is not found. After that, we perform prefix searches. The trie confirms that the words with the prefix CA exist, while no word starts with XYZ. Finally, we delete car and search again. As expected, car is no longer found, but card is still exists because deleting one word does not affect other words that share the same prefix. That's all for me.
Assalamu alaikum. I'm Muhammad Atikur Rahman. I'm going to talk about trivariants. A trie is a tree structure used to store and search words very quickly. There are three main types of tries: the standard trie, and the compressed trie, and the suffix trie. In this presentation, I will explain how these three types works. First, let's look at the standard trie. This is the most basic version. Here, very Here, every note holds exactly one letter. When you go from the top to the bottom, the letter makes a full word. It is very easy to understand and build. It is great for searching word using prefixes, but it has one big problem. It uses too much memory. Every note makes space for 26 pointers. Every Even if we don't use them, most of these spaces stay empty, so a lot of computer memory is wasted. The second try is compressed try. To fix the memory problem, we use the compressed try. It is also called the uh, pressure try. In a standard try, there are long chain with only one child node. The compressed child joins these nodes together, so one edge can hold a group of letters instead of just one letter. Its biggest advantage is saving memory. It uses much less space but keeps the same fast speed. Then the third try is suffix try. This one is different. It is built from one single text. We take a text and find all its This then we put all these endings into a compressed trie. Why we do why do we do this? Because it makes searching inside a text very document. You don't need to read the whole file. You can find it instantly. But its main problem is high memory uses. If the text is very long, it creates too many suffixes, and that takes a lot of space. So this is the try variant, and most common part is advantage of try. Let's look at the main advantage of try. First, it is dynamic. It only creates a node when we add a new letter. We don't need to block a fixed memory size at the start. Second, we share memories. Words that start with the same letter use the same nodes. This saves a lot of space. Thirdly, prefix search is super fast. If we want to slow automatic words, the try finds them immediately without searching the whole database. And the another part is disadvantage of try. Every data structure has some bad points, and try has them too. First, it has a high memory uses. Each node is try has an array of 26 child pointers. It does not matter if we use them or not. Secondly, the exact mass searching a try can be slower than a hash table, and a hash table can find a word in big O1 every time, but a try must always go through the word letter by letter, which takes more steps. So this is my presentation. Thank you.